So hello guys, Rishit is here for today's session and it is on TensorFlow. So now he'll be starting the session soon.
Hi all. Okay, so before we start the session, uh, I, I I would just like to tell you that I have switched on captions from my side, so you can see the captions down here, and you do not need to switch them on from your side. And the workshop will be more on implementation things, how you can make a project all by yourself, and it's no problem at all if you don't know what TensorFlow is. That's what we'll be doing. So let's get started now. Uh, uh, Hello everyone, I'm Rishit Dagli. I'm a TEDx and a TEDx speaker. I'm also a Google certified mobile site developer, Intel AI scholar. I manage two communities here in Mumbai too, and I'm a two-timer GCP champ too. So if you want to find me, here are some of my links. You can find me on any of these links. I am almost there on all social medias. You can find me on LinkedIn, GitHub, Twitter, anything else you could think of. You could find me on any of these. So away with me and let's start. So first, I thought I would give you all the code and the links you need. So for people who want to live code along with the session, can move on to this link. It leads you to a Google Colab file where the code is already written. What you can do is create an empty file and try to put in your code from there. And for a lot of people who may be viewing this from their mobiles or mobile devices, sit back and enjoy the show, gain a lot of knowledge, as the slides contain a lot of code, so you'll just feel like you're coding yourself. You could also try these codes for yourself after the session. Okay, so let's continue. So usually I take this analogy. There are two people in the world. Um, so one is a section of people who know AI, who know a bit of AI, or who even know AI, and they say that a, uh, and then there are these other kind of people. Let's get to these kind of people first. People with no idea about an AI say AI will destroy humanity and things like that. And then there are other kind of people who know AI, who build an AI algorithm, and they think why their AI algorithm to differentiate between a cat and dog is classifying a cat as a dog. Okay, so away with jokes and let's get started with some of these things. So, for today, what we'll be doing is we'll be learning about some of convolutional neural networks, TensorFlow, and things like these. If you don't know what these are, it's completely okay, as I said earlier too. And we'll be live coding with a project. So the dogs versus cat, the example which I mentioned now, we'll be making a project for that. We'll be we'll make a model, we'll make a code that can classify dogs and cats on with some deep learning algorithms. So this is the data we'll be using. We'll be using a Kaggle data set, which has around 2000 images, around 3000 images, sorry, for dogs and cats. And it's pretty good for beginners. So we'll work with this. So first, before I start into how you can do this and all, uh, let's see what traditional programming is and what machine learning is. So first, we get to the idea of traditional programming. Sorry. Yeah. First, we get to the idea of traditional programming, which is essentially what you do is you pass in your algorithm rules, you pass in your algorithm the data, and it figures and it gives you the answers out. So maybe you have a bunch of if else statement, you write the things in maybe C, C++, Java, Python, I don't know, so many languages. So, uh, what you would do in this would write a couple of if and else's for dogs versus cat, and write that maybe if my cat has some of these features, then it is a cat. If my dog has some of these features, it is a dog. And you would write a lot of if and else statements. That's what we would do with traditional programming. Let's see how machine learning is an altogether different paradigm. What? Okay. Yeah. What machine learning does is it ML dan actually turns this around and it flips the axes for you. So what it does is, okay, yeah. So what machine learning does is it takes in the answers. It takes a lot of answers like how do cats look like? How do thousands of cats look like? How do thousands of dogs look like? So that's our data. It knows that this is how a cat look like. So it has maybe an image of a cat, and it knows this is how a cat look likes. So that's our answers. So in a machine learning algorithm, you pass in your answers and your data, and the machine learning algorithm, instead of you writing all the if else and things like that, it gives you the rules out. And uh, so what it essentially does is, with the data and answers, with a lot of data and answers in reality, the machine learning algorithm figures out some rules to map this data into your answers. So again, machine learning algorithm tries to find some rules to map your data into answers. And let's see this in a greater detail with some more examples and things like that. Let's see how this would be in a real life scenario. So let's talk about activity detection. How would you write a code to say that someone is walking? So maybe you tell me I have access to the speed of the person. So what I essentially do is I just say if the speed of person is less than 4, he's walking. That's all the problem. That's cool. Then, oh, sorry. Yeah. Then what you have is there's another person, your friend, who's running. So what do you do next? You say, oh, no problem at all. Uh, I'll just say if the speed is below some threshold value, let's say 4, the person is walking, else he's running. I solve the problem again. Okay, what next? Biking. If the speed is between 4 and 12, he's walking. If the speed is less than 12, uh, if the speed is greater than 12, he's running, and else he's biking. Okay, cool. But now you have another friend who says to you, I like golf. Now, golf involves a lot of walking around. So, how do you do that? That's when your traditional machine learning algorithm just gives up. So, what do you have for aid? You have machine learning to aid you. So, how would this work in a scenario like this? You'd have a lot of images. You'd have a lot of so first, before we start with that, make sure you know this diagram and understand what this diagram shows you, so that we'll be using this quite a lot, and we'll be using this analogy quite a lot while the session. So make sure you understand that you have a complete hang of this diagram. Moving on. So what you do is, all you need now is sensor data from people who are running, walking, biking, and even golfing, which in my case, uh, in sort of golfing, you have some data in forms of zeros and ones. Maybe you have images and things like that. And then you have your labels too. So you give the computer a lot of images with labels saying that this is how walking looks like, this is how running looks like, this is how biking looks like, and things like that. With a lot of images, your machine learning algorithm will figure out some rules, some pretty elegant rules. And then it will efficiently allow you to predict all these kinds of data. So you are in effect telling a computer, this is what walking looks like, this is what running looks like, and it tries to identify some rules from it, which can help you for predictions in unseen data. So maybe you then have another image which does not look like any of the earlier images and is a walking image. Your machine learning model can easily do that. So that's the beauty of it. So having discussed the problem with traditional algorithms and how machine learning flips this around, it would be best now to discuss what we'll be doing today, uh, and how we'll be solving this problem in practice. So we'll be using TensorFlow to do this. I think you might have figured that out by now. Okay, so we'll start by building a data input pipeline. What this means is, what this means is you have a way to feed your data into your machine learning algorithm. So I, of course, need a way to input my data into my machine learning algorithm, because my machine learning algorithm essentially stands on the data. It needs a lot of data to work with. We'll see how we can use TensorFlow classes and TensorFlow functions to do this efficiently. Then you'd want to build a machine learning or a deep learning model. In this case, we'll see how we can use convolutions and things like that. So then we'll build and test our model. Then we'll see if our machine learning model is overfitting. So what overfitting essentially means is, you have very good accuracy. Your machine learning algorithm does very good on the data you have given it. But when you put it out into the real world scenarios and it comes across data which it has never seen before, your machine learning algorithm fails. We want to prevent this, right? Because machine learning, with machine learning, I want to do something like predict future values, or maybe predict things on data it has never seen before. So we'll see how we can reduce overfitting. This is a pretty important thing. So these are few techniques to avoid overfitting. We'll see them in great detail. So without further ado, let's move. Okay. Yeah. So first, as I earlier said, machine learning or deep learning algorithms stand on data. You need to have a lot of data to work with. You need to have good quality of data too. So it's always best to first understand your data. Let's do this. So, as I said, we'll be creating a project for cats versus dogs. We'll do a cats versus dogs classification. So we essentially have two splits in the data: the training split and the validation split. So what a data would look like is, you have this folder called training data, you have this folder called validation data. Inside both of them, you have another other folders called, okay, you yeah Okay, you have other folder called cats with a lot of cat images, dogs with lot of dog images, and so on for the validation data too. So this is what a data would look like. This is a training split of the data, and this is a validation split of the data. We we need to make these two splits. So training split is data we directly give it to the model, and the validation split is the data we'll use to test out our model, see, experiment around with the model, so we get a good model architecture. So if I do this on my data, I get something like this. My training cat images are 1,000, my training dog images are 1,000, and my validation images too. So in all, I have 2,000 training images and 1,000 validation images, giving me in all of 3,000 images to feed to my machine learning model. So before we write any program, let's start with the inputs. Nothing new. So we'll start by importing TensorFlow, and we'll also import TensorFlow.kdis to make our neural networks. We'll see how to do this. You'll see how to do this easily, and also some mathematical calculations and plotting libraries, so we can visualize our data well. So these are few parameters according to the data set. So all images are different. If you take an image from your phone, if you take an image from your webcam, if you take an image from DSLR, all have different sizes, right? Some might be some might have a huge size, some might have a small size, different number of pixels. So what essentially I'm telling you to my computer is these are the uh okay, yeah, sorry, this is the image height and this is the image width. So my image is 150 pixels by 150 pixels. That is my each and every image in my data. Leave this epochs for now. We'll discuss batch size. So what batch size is that we'll not load all of the data at once. We'll not feed all of the data at once to my neural network. Instead, I'll make small subsplits of the data. So maybe I can do something like, uh, let's say I have this data over here. This is my data. Let's say for now, these four boxes are my data just for representational purposes. And I say I first put in this box into my neural network. I then put this box into my neural network. I then put this one, and so on. So this is essentially what we do with batch size. I'm telling it, you take 128 images, 128 images, and so on. Okay. So I feel these were the few parameters you need to set at the start. So now we move on to a very important part called data preparation. So I cannot just put the data into my neural network or into my machine learning model. I need to do some transformations into it, some changes with it. Let's see this. So we'll cover the complete process of how you get your data into a ready to put in data. So first, we'll read images from the disk. Yeah, that was an obvious one. Of course, you need to read your images. After that, you can get your images. Then what we need to do is, it's essentially an image. The computers understand zeros and ones, right? So I'll decode these images and as per their RGB content and convert it into a grid. So this is just something like that, and converting them into floating point tensors. We'll not see a lot of this now. So when converting into RGB, my image values range between 0 and 255. It's always good for neural networks to scale the 0 to 255 into 0 to 1. neural networks prefer to deal with small input values, and this would be it's good if we can provide them small values. So I've just rescaled all of them from 0 to 1. Let's see how you do this. TensorFlow makes it very easy for you to load the images off the disk. So there's just something called data generator, image data generator. You simply import the image data generator and just put it something like this. Train image generator is equal to image data generator, and you put this rescaling factor. So we just discussed that for my neural networks, they deal well with smaller values. So I want to give them sufficiently small values. I want to put the 0 to 255 range into 0 to 1 range. So the argument rescale 1 dot slash 255 will do it for me, all just in one line of code. And it also uh, prepares the image data generator class for me. Let's see next. So what essentially this flow from directory does is it tells you to now load the images into the memory from the disk. So after that, I would so you remember that directory architecture which I had shown before. So I'll just tell it where to find the images from. That is my directory. So I'll tell it you find all of the images in a folder called trained directory. The target size, as we had mentioned, what is the image size? I need to specify it. We had also talked about batch size. All you do is simply make an argument for batch size, and TensorFlow handles it all for you. Okay, so what is class mode equal to binary? This was a simple question. I'll give you a minute, a sec maybe, to think about it. Okay, if you thought that, if you thought something like, I have to do prediction between whether an image is cat or a dog, that's true classes. What's true called? Binary. If you thought that, you're completely correct. And that's what the class mode equal to binary tells it. And similarly, all the same code, I'll put it for validation data. So you remember the two data splits we had made? I'll just put it, I'll just call it for validation data too. Instead of the train directory name, I'll just put validation directory. Okay, so we have our data ready to put it into the neural networks or our model. Let's understand how we would make a model in TensorFlow. Let's do this. So we can easily make our model in TensorFlow by calling the sequential API. So what the sequential API does for you is it it's a Keras submodule, and what it does for you is it tells you that I want all of these three layers in a sequence. So that's what essentially sequential means. So first is the flatten layer. We'll see what all of these layers mean and when to use what, but this is essentially how you define a super small neural network. We'll see this in a greater detail. So starting with this input shape. So we earlier discussed that my image size was 150 by 150. So why is this, what is this 3 doing over here? Any guesses? Okay, so what exactly the 3 is doing over here is I have an RGB image. So 150 by 150 by the 3 values for the things in RGB accordingly. That's what my input shape tells it. Forget the flatten for now and the dense for now, but the number which you see over here is the number of neurons in it. And this is the 5 into neurons. Let's hack into this and see what do the number of neurons mean and things like that. So this is essentially how a neural network looks. You have all of this data over here. You send it to neuron number 1, or as in our language called neuron number 0. You send it to neuron number 0, which essentially is a mathematical function, and you get some output from it. Similarly, you send it to neuron number 1, get some output from it. Send it to neuron number 2, get some output, and so on. And then, uh, so uh, as I told, let's see this image again. So first I have these 5 and 2 neurons, then these 2 neurons. So what this means is here we have all our 5, 1, 2 neurons. And this is our last 2 neurons. So first I put in the data to my neuron number 0 and neuron number 1 and so on, and get all of the data into one neuron, do the so once this is over, I do the similar for the second neuron over here, and so on. So we just build a super simple neural network. Let's see what this code does for us. So we discussed of so before coming on to this code, I discussed with you what a neural network is, how it works, how those 5 and 2 neurons map into those 2 neurons at the end, and things like that, how they're essentially mathematical functions. So neural networks work on trial and error. What the neural network will try to do is it will try to get an optimal relation or the rules for my data. It will make a guess for the rules. So then it will see, okay, my guess wasn't that good, so I need to improve on my guess. The neural network then improves on the guess and does this continuously to bring you closer to the final output. So at the end, you'll have a good guess by doing trial and error, and by continuously doing these trial and error things. So that's exactly how a neural network works. So we discussed about how you do the trial and error thing, but we didn't actually discuss about how neural network does this. And so there are in fact 2 functions to help in this, namely the optimizer function and the loss function. So optimizer and loss are just 2 functions which tell the neural network how to make the guess, how to put your guesses more accurately. What the loss does is it tells the neural network how good or bad my guess was. The optimizer then takes data from the loss function and makes a new guess on basis of these data. This new guess should be better than my previous data. And I continue doing that for a lot of time. So one cycle through this is called an epoch. So I told you earlier to forget about it for that case. Now we are revisiting that. So one cycle like this is essentially called an epoch, and we want to do this multiple times. So I go on to create better guesses. So there are quite a lot of optimizers for us to use. A lot of academic research is done on optimizer and loss functions. So we'll use an optimizer called add-in. You do not need to know what goes on inside add-in and things like that. We have a lot of other optimizer functions too, like RMS prop and many more. We have NADM, we also have NADM and many more optimizers like that, a huge array which TensorFlow provides you. But for now, we'll stick to Adam. We'll also see how you can use another optimizer, but we'll see that part at the end. At the end, we'll leave it for the end. So now I've defined my optimizer. and my last function. So I now need to start my training. That is, start making the guess, start improving on the guess. So what I'll do is I'll call a method called model.fit. I'll pass in my data, we'll see what goes in there in some time. And then I'll also pass the epochs. So as I just said, epoch is one complete cycle like this, and you do this multiple times. So I define my epochs, and we are also using, so at the end, this is an image. So we want to extract features from the image. So what I'll do is I can define some filters for my image. We'll see what these filters mean. But essentially, a filter is an array like this. It may be a 3 into 3 array, 5 into 5 array, 7 into 7 array. So now you might be thinking, why did I only say odd numbers? So it's usually a good practice to use a odd number by odd number filter definition array, but you can of course try it out with some even numbers too. So what this filter will do for me is it will, so let's take uh, one of these examples. Let's take the pixel 64, or for this matter, let's take the pixel 192. It has a lot of immediate neighbors, so will be good for me to explain. Let's take the pixel 192. So for each pixel in the data, for now let's consider 192. I'll take note of its immediate members and apply this filter definition on it. So when I apply this filter definition, my new pixel values will look something like this. So I took note of all the immediate neighbors for this, for the pixel number 192. So so when I came onto the pixel called 192, I saw that okay, zero is a neighboring pixel over here. So I go to the same neighboring pixel in my filter definition. What's it? -1. Okay, so I'll multiply 0 into -1. Similarly, I'll do for 64, which is an immediate neighbor, 64 into 0, 128 into -2, and all of that with the immediate neighbors and add them up. So that will be my new value for pixel number 192. We'll see how this helps us, but now you understand the intuition behind this. Let's see how this will help us. So this is an image, a sample image. I applied a filter looking something like this on it. And this is the output image I see. You can see a bit of grayscaling and things like that, but take a close look into it. What's it? You can see all the vertical lines in the image being highlighted. So that's what filters did for you. With just the right definition of filters, it highlighted all the vertical lines in the image for you. We can simply do this for horizontal lines too. I just reverse the pixel values, and now you can see all the horizontal lines in the image are highlighted for you, and that's cool. So now, having talked about filters, we'll make our way to convolutions. So, uh, so these are my convolutional layers. So what convolutional layers do is they are good at finding out certain features in the image. So I'll take an example. How do you say if something is a purse? When you take a look at the image, give it a thought. What you see is, you maybe see, oh, it has those handles above it, and it looks something like a bag, but with the handles and a particular style of design, it looks like a purse. That's how you identify a purse, maybe, and maybe all other things too. All of this goes into your mind, of course. So convolutions are all about detecting features in the image. You try to detect these kind of different features in the image. So this is again the number of neurons in the network. This is the filter size and so on. So we'll discuss what activation functions are in a while, but just forget it for now. And let's take a closer look what the max pooling does for us. So followed by convolution layer, you should always have a max pooling, as convolution tend to increase your number of parameters. And what a max pooling does is, let's see how this works. So how a max pooling algorithm, sorry, yeah, sorry. So what a max pooling algorithm would, so here I mentioned max pooling 2 comma 2. Let's see how that would work. This is my image. I'll take a 2 comma 2 square from it, and out of all of these values, I'll remove all the values except the one which is highest. I'll take this highest value and put it in to create a new image. Similarly, I'll do for all of these subsets. Similarly, I would do for all of these subsets and create a smaller image, but with all the essential features highlighted. So let's see a max boolean 2 comma 2. So this is what happened after I applied filters, after I applied max pooling. You can still see the same almost the same output. All the vertical lines are highlighted, but your image size is reduced to a fourth. And that's some very good progress. In very huge data sets, you might not have enough memory to show all of this. So this just reduced your image size, your data size by 4 without giving you a loss in uh, detecting the features. So you might have also, so I defined 3 of these convolutional neural networks. You might have also seen this flatten. Okay, what does flatten do? Let's see it now. So this is what my pooled feature map looks like. It's always good for neural networks to flatten this out. When I say flatten this out, I essentially mean to convert it into a 1 into X array. So TensorFlow handles all of this seamlessly for you just with a line of code called flatten. And this is essentially what flatten would do for you. It would convert this 3 comma 3 grid into 1 comma x into a 1 comma x array. And uh, and this is quite helpful in real world applications too. We'll see how this helps us too. So what the padding equal to same does is, so if you take a closer look at how convolutions actually work and how they extract the features, uh, the padding equal to same tells tells the network to uh, okay, yeah, I got a good way to frame it. Just got a bit lost with some English in between. Ha, just a bit of thing. So what padding equal to same will do for you is it will fill out the missing places in the data for you with the padding equal to same thing. You just pass an argument just like that, and TensorFlow handles it for you. Another important thing to note about features is, let's say you have a 4 cross 4 input. When you apply a 3 cross 3 filter, let me demonstrate this in a better manner. Yeah, okay. So when you have this 4 comma 4 image and you apply 3 comma 3 filter on it, the filter would work something like this. Okay, just, yeah, the filter would work something like this. It will take out these three, take out these three, and so on. So as you might have seen, let's say a pixel value here 0 comma 0 has no immediate neighbors. So when it has no immediate neighbors, you'll be forced to cut off your data. You'll be forced to lose some of your data, and you'll finally end up with an output 2 comma 2. So this is an important thing to know in while using filters and convolutions, as you might make some serious mistakes if you don't consider this. Okay, let's move on. Um, I'll just quickly remove all of these annotations so it becomes easier for you. Yeah, okay. So, yeah. So there was this thing we left earlier called activation equal to ReLU or activation equal to sigmoid. Let's exactly see what this activation function is now. So there are quite a lot of activation functions. This is the sigmoid activation function we discussed, the ReLU we were using. What this does is, what the ReLU does is, it prevents your neural network output to go in negative values. So you can define it as if you have a positive value, ReLU will keep it. If you have a negative value, ReLU will convert it into 0 and output it. So usually ReLUs face a problem called vanishing gradient problem. We'll not discuss much into it now. Uh, and on and I'd say a substitute for it was made by leaky ReLUs and tan hyperbolic. But we do not need to know all of that. We'll focus on the practical aspect, when to use sigmoid, when to use ReLU, and things like that. Let's see them. Okay, so here in the last dense layer, what I have is one neuron with a activation function sigmoid. What sigmoid will do for me is, so at the end, I want a prediction, dog or cat. So I have one neuron, sigmoid will output the value as in between 0 to 1. So I can know that if my output is between 0 and 0.5, it is more probably a dog. And if my output is between 0.5 and 1, it's more probably a cat. So that is what sigmoid does for you. So this is what we discussed earlier. I have added a thing to this which is called metrics equal to accuracy. So what this tells the model is, you also need to include the so you also need to output me what accuracy my model is at. So this is also pretty helpful when debugging your networks. Seems to be pretty helpful when debugging your networks. So in TensorFlow, if you do a model.summary, we'll do all of this in some time. We'll see how you can do this. But for now, this is our complete neural network architecture. This is what we just made. We went through convolutions, we went through max poolings, flatten layers, what dense layers do, and now we have a complete neural network with us. And we also use some convolutional layers. So earlier we talked about model.fit, the model.fit method with epochs. I'll make a slight change to it. So instead of using the model.fit, as I was using an image data generator earlier, you remember that? We use that to load in our images. So I'll use a fit generator instead of fit. So we left some of the other parameters. Then, as we didn't discuss about that in great detail. We just discussed about epochs. So what this does is, you have so you pass in the training data, you pass in your validation data, and you pass in your steps per epoch. So ideally your steps per epoch should be the number of training samples by the batch size. uh, but there are no bearing roots to it. This is what you ideally should use, and we'll see that in a while. So I train my model on these training. So when I train my model with this, what I see is when I train my model with this, my training accuracy keeps on increasing. You can see the curve over here. Okay, just a sec. Yeah, my training accuracy keeps on increasing. The blue curve over here. But my validation accuracy, so my training accuracy goes over 90%, which is too good. But my validation accuracy is pretty low. And that is a very bad scenario. It tells you that if you deploy a model into a real world scenario, your model wouldn't probably work well. So this is the case called overfitting. Let's see how we can reduce this. So as I told, this was a case called overfitting. So this happens when you have a small number of training examples and your model learns noises from the training examples, like wrongly classified sensor data and things like it. So the best way to avoid overfitting is you add more data to it. But the problem is data is the new oil. Okay, so if you compare the oil prices now, I'm not talking about that. Yeah, off with jokes. Uh, Data is the new oil. It's costly to get data. Sometimes you just can't get data. So it's good to know what other methods we can use. One is the data augmentation, and we'll architectures that generalize well. We'll see both of them quick. What data augmentation does is it apply some transformation to your pictures. So let's see this. So if you have an image like this, I apply a horizontal flip to it and make it two images. I feed both of these images into my network. And now I don't have different data, but I just kind of created two kinds of data, two kinds of pictures from one image. So this was data augmentation. There are some more things you can use. What I've done here is I've rotated an image and created another image. I've rotated it by 45 degrees, as you can see over here. You can also zoom into the image and do things like that. Let's put all of these transformations we saw. We saw rotation range, we saw horizontal flip, zoom range, and similarly, we also have a height shift and width shift. That is pretty self-explanatory, so I didn't show an image for that. So, okay, sorry. This is essentially all put together, your training data generator put together. And another method which I discussed was architectures that generalize well. So we can use a dropout layer. What a dropout does is it, as the name mentions, it drops out some of the output units from an applied layer. So how you do this? You just add this dropout layer and it shuts off or it removes 20% of the neurons. So other neurons can learn some features well, and you can generalize your model well. So now you're maybe thinking, okay, that's all well and good, but I want to make predictions. And this is a simple way for you to make predictions. We'll not go into this, but I want you to see this part, the lowermost part. What this tells you is I made a model, and there's a cool thing called model.fit. So model.predict, I'm sorry. Model.fit we already discussed. You can see this model.predict, right? What model.predict does is if you give it a new image, it will predict which class the image belongs to with the neural network. It tries to create a prediction from the neural network. So as we discussed, if it's greater than zero point 0.5, it's a dog. If it's less than okay, if it's less than 0.5, it's a cat, and so on. So you just created a convolution neural network all by yourself. And you could also test it out. Let's see this in action. Let's see this in code, how we can achieve this in code. This is the notebook link for the code. It's called bit.ly deal with tf. So I'll just flash on this link for a second. You can see the complete code over here. Okay, I feel most of you might have noted down the link or something like that. So let's go on to the code. Yeah. So this is essentially how your code would look like. There, it has all of the things we just mentioned. This is, I'm just downloading the data in extra cell. I just downloaded the data. And then you have all the things which we just mentioned, augmentation and things like that. However, in this, I've done something cool for you, something you can try out too. We discussed about uh, we discussed about 3 convolution layers. I put in 4 convolution layers in the code. So 1, 2, this is the third one, and this is the fourth one. So I put in 4 convolution layers. You can try to experiment around this. You can try changing some of these values to see which give you a better accuracy and get a hang of it. What I did is I tried to increase the convolution layers so to maybe see if we can get a better accuracy. And I improved my accuracy by almost 5% and my validation accuracy too. So that was a good win. So I thought that it's better to use 4 convolution layers. I've also included another optimizer for you. So as I told, yeah, I'll also show you how you can use some other optimizers. So this is how I've shown that how you can use the RMS prop optimizer. So work with this, replace it with Adam, see how things go out, and that's for you to experiment. I'm just augmenting the data over here, flowing the data, and here is the final model fitting. So there's just an added line of code. I don't want to go through all of this. Instead, what I'll do is I'll plot my model results. So here is my plot. Here is a training and validation accuracy plot. And I can see my training and validation accuracy is around 80%, which is good. My validation accuracy, which shows how well can my model do on things which it has never seen, is also good. So we have done a pretty good progress. The loss here is a bit noisy. It has quite a bit of noise, a lot of fluctuations. So that's something we need to still improve on. I leave that for you. You can do some tweaks around with the code and things like that. So that was about how you can create a simple convolution layer to classify dogs and cats all by yourself. I hope that you also got to know about how convolutions work, how dense layers work, how TensorFlow works, how TensorFlow allows you to do all of this very easily and things like that. I would recommend you to go over this code once, try it out for yourself, and you would have a hang of how things work around. And then start working on some other data. With all of this, you'll be well equipped to work on other kinds of data too. Uh, okay, I'm sorry, I just made a mistake. So the link which I showed you, uh, so there was a link which I am really sorry uh, a, for a slip of tongue by me. So the link which I showed at the start of the workshop was the link for the code through which you could find this code. This link is if you are really interested into how AI works, knowing more about AI. Here is a blogging series I run called Deep Learning with TensorFlow. You could read this blogs to get a more in-depth understanding about it and things like that. So sorry for that. The earlier link which I shared was the code link, and this is a link to know more about the blog, about more in deep about this. So with that, I guess you now have a very good idea about convolution neural networks. You can create one all by yourself and start working on some other data too. So here are my social links again. With that, I would love to take any questions if you have any. Just type them in the chat, or as you might like it, I'd love to answer some questions if you have any.
So guys, is there any queries? If not, you can also ask in the WhatsApp group. Rishit is available in the group. So thank you, Rishit, for the such a technical session, as it had gone a little technical for us, as we aren't having any of the knowledge about TensorFlow. Thank you for the session.
Thank you. Thank you for attending. Work with different data, and if you get stuck, I would be happy to help. Try to work your way around the code. Thank you.
Sure.